All right, so good morning, everyone. I was leading the Edge AI project, and this is our team. I was helped by Adnan Ashraf. He is a master student in UCD, and I was supervised by Dr. Deepu John, also from UCD, and of course, Oshin from CEDAR. Many thanks to our company partners who all voted for this project. And without further ado, I will straight away get into the demonstrator. Talking about Edge AI, it's necessary to highlight what we are just doing in the project. Edge AI is about running neural networks or machine learning algorithms on resource constrained hardware devices or embedded systems. So you know that the neural networks, which are like hundreds of megabytes of memory and needs a lot of computation, deploying them on these devices, which are really small, have less memory and have less computational power, is a challenge. And that's the challenge Edge AI tries to address. And in this demonstrator, what we have done is we have implemented a complete pipeline of the Edge AI project. So starting from the data set, designing a neural network, training it, then pruning it, quantizing it, generating the embedded code, and finally deploying it on an embedded system. So we have implemented all this for this project. And now I'll take you to our demonstrator, which is our web application. And this is the homepage of the demonstrator. And it has the same diagram which I showed you. So even though we have implemented the whole project pipeline, but for the web app, what we have done is we have chosen this green part of the pipeline and made it automatic. So what this demonstrator can do, that if you send your neural network to this demonstrator, it will quantize it, generate the embedded code for it, and then you can use that embedded code to run on an embedded system. And to demonstrate this quantization and generation of embedded code, we have chosen heartbeat classification as our example problem. So there's this dataset called MIT BIH dataset, which is openly available. And our problem is to classify a human heartbeat into one of these five categories. It can be normal N or S, V, F, and Q. And for doing that, firstly, we designed a neural network. So this is the architecture of our neural network. It has three different inputs, and it has a variety of layers, your convolutional layers, fully connected layers, and in the end, it classifies heartbeats into one of these five categories. Now, coming on to what this demonstrator does, it is that it picks this model up and quantizes it. And why do we need quantization? So the first reason is many of these embedded systems can only do integer arithmetic. That means they can multiply and add only numbers like 1, 2, 3, 4, 5, like integer numbers. But all these neural networks have decimal numbers, or what we call floating point numbers, like 4.5, 5.5, and so on and so forth. So to run these neural networks on those embedded devices, you have to convert them from these floating point numbers to fixed point integers. And that's what this demonstrator does. And it gives you three options for this quantization. You can quantize them into 8, 16, or 32-bit numbers. That means each and every parameter of this neural network can be represented by 8, 16, or 32-bit word, depending on your choice. So let's get into it. Let's choose 16-bit quantization and just hit the start quantizing button. This will take you to the results page, and it will take about a couple of minutes. So what we'll do, there is a previously we had run some experiments. I'll show you those. And by the time this will also be completed. So if I click explore on one of our previous rounds, this takes us to the results page. And again, on the results page, you will see the architecture of the network. This is just for users' ease of use. And then some description of what the results are. And then we have these 5 result tabs. And in these results tab, we'll try to explain like what not just the output of our model, but also how things were done within the model. So take, for instance, statistics tab, and let's take the example of inputs. We have 3 different inputs for our model, and each of these inputs have to be quantized. And the very first step in quantization is deciding the Q format of quantization. Now, what does Q format means? It's very simple, actually. So you can use only 16 bits to represent each of these inputs. Q format tells you how many of those 16 bits would belong to the integer part of your numbers and how many to the fraction parts. So for the heartbeat, our algorithm automatically chose Q format of 4.12. That means 4 bits out of those 16 bits will be used to represent integers, and 12 will be used to represent fractional part. So how does an algorithm do that? It takes in the minimum and maximum range of those numbers and tries to see what minimum number of bits is needed to represent that whole range. And we do that not only for all the inputs, but for each and every layer separately also. So this is our very first layer called convolution one layer. So it takes the weights plus the histogram and then automatically calculates what the Q format for weights would be. So here it's 1.15, same similarly for biases and then for activations also. So what activations are? After each and every layer, you also have an activation, and the output of that activation function needs to be quantized too. So that's what this activations present. And we have done this for all the layers here, and you can see the outputs here in this page, in these tabs. So after the algorithm has automatically calculated all these Q formats, what it does next is it actually quantizes all these parameters and puts them into these two tabs called weights.header and inputs. Some of those who are familiar with embedded programming will immediately recognize this. So weights.header file is like a file which has all your variables which store weights and biases of the network. So remember I showed you convolutional one layer. So this array is of the weights of that convolutional one layer, and you'll see these have been quantized to integers. All these are integers if you notice. Similarly, there the convolutional two layer, convolutional two bias, and all the other layers of the network have been quantized here. And there are some other parameters needed, like the stride of your convolution, etc., which are also present here. Then we have also quantized the inputs. That was the first diagram I showed you. So here is a sample of 10 different inputs which have been quantized. These will help you to run and check your embedded code on your device. You will notice both of these tabs have these copy to clipboard button. So you can click that button and this code would be copied. And then you can switch to your IDE where you program your embedded system and copy paste this code like I'm going to do now. So here is a copy paste of the code. Similarly, you can do for inputs. I've already done that. And the last tab is our embedded code itself. So for this demonstrator, we have used this embedded system called NRF52840 SoC, and it uses an ARM processor, the ARM Cortex-M4 processor to be precise. And ARM has this library which has functions for neural networks which are custom built for their processors. So we have used this library, and our algorithm, what it does all the quantization, converts the number to the quantized form, and then generates this code also automatically using ARM's library. And there were some functions missing from the ARM's library also, like 1D convolutional layer. So we also added all those functions. So if you scroll through this code, you will find everything in there, and you can find the neural network also in here. So this is our neural network function, and you'll see this is our layer one convolution, and this is our convolution function, and then there is the activation function, and so on for each and every layer. If you go to the main, that's your entry point for the program, you will see that our program reads those inputs from a file, which I just showed you, runs inference on those, and writes the prediction to an output file. And you can do the same thing here. You can copy this code to your embedded IDE and run it there. So I can do that out here. So one thing which is of consideration while quantizing is the performance after quantization, and that's how you judge whether a quantization method is useful or not. And that's also where the second benefit of quantization comes in. So I choose here to represent my quantized model with 16 bits. So each and every parameter takes 16 bits, and the unquantized model takes each and every parameter takes 32 bits. As such, if you compare the size of both these models, you'll find that the quantized model is just almost half the size of your unquantized model. So you save almost half the memory needed. And one of the things to consider is if we are quantizing, is there a reduction in the accuracy of the model? And this is what this row shows here. Fortunately, for this method and for this quantization scheme of 16 bits, we did not see any reduction in accuracy. So quantized model showed 81.2% accuracy in this test set, which is the same as your unquantized model. And not just that, like 99.9% of the predictions of our quantized model matched those of the unquantized model. So it's pretty good, given that we followed like a simplistic quantization method. And you can actually check if you play with the demonstrator, you can check other bits, other quantization schemes, as like 8 bits or 32 bits. So what I'm going to do next is actually going to show you what happens after this demonstrator. So you have all this embedded code ready. After this embedded code, you paste it into your IDE and you upload it to your embedded development platform or whatever chip you are using in layman terms. And that's what I'm going to do. So I pasted all that code here in this IDE, and I'm going to build it and upload it to my board. So I build it and I run it, and now it's running on my boards. What I'm going to do is stop sharing my screen and just concentrate on my webcam. All right, so you can see me. So I'm going to turn my webcam here, and you will see the board here. So this is the chip that we are using to run inference of a model on. So I've uploaded the program on that chip. Those sample inputs are also in this chip. And this chip has been hooked up to an oscilloscope, and the output of your neural network is appearing on this oscilloscope. So I want you to concentrate up here on this oscilloscope now. I'm going to pause this oscilloscope to show you what's happening here. Yes, so there it is. So what I've done that for each normal prediction of a neural network, the oscilloscope shows a spike. So you see these small spikes here. But then for each abnormal beat, it shows this kind of a waveform, which is obviously very different from a spike. And remember those 10 sample inputs I showed you? So these are all those 10 output sample inputs for which our board is running live inference for, and I've put them in a loop so that we can continuously see the output. And one of those 10 beats is abnormal. So you'll see all these normal beats out here with spiky things, and then you will see like a one non-spiky thing. That's your not normal beat. That's the prediction of the neural network. So I think, yeah, this is all actually. So in our demonstrator, we have used only one model to represent all this, but one neural network, but it can be extended to other neural networks pretty easily. So if you have any network which you want us to try, do send us and do contact us. And if you have any questions, do the same. So I think that's all from me.